Good afternoon, everyone. My name is Sushil Kineker, and I'm the Chief Engineer of the WEAT Suborbitals Company, a subset of the Aerospace Vehicle Design 2 class. Today, my team will be presenting our senior design capstone project results. Before we get into the details of the project, some context is necessary. We've already established that flight has always been considered as a prestigious concept ever since the first flight. In the past century, mankind has taken to the skies and has started venturing out into space. First man in space, first man on the moon, and a government program designed around making space accessible to the public are feats which were impossible a century ago. Private companies such as Blue Origin, SpaceX, and Virgin Galactic have also started investing in the space industry, since the government-run agencies lack the coordination for a profit-making program. But today's technology is still limited as space launch systems are vulnerable to external factors and are not that convenient. A single-stage space vehicle which can employ horizontal takeoff landing methods and which can operate in and out of commercial airports is now a feat that the future holds and is the key to making space more accessible. The team was formed by 13 engineers and they were split into individual disciplines. These consisted of synthesis, aerodynamics, geometry and landing gear, stability and control, propulsion and fuel system, weights, volumes and structures, cost, safety and certification, aerothermal and TPS, and trajectory and performance. Simulation was also added after an interest in visualizing the overall trajectory was expressed. A timeline was created to track the company's overall progress to develop our new aircraft aspiration. The mission profile was investigated by the entire company to highlight important concepts from the different phases in the mission profile. A questionnaire was created to categorize the business case questions and the engineering case questions, which were used by the engineers to create their interdisciplinary analysis. The mission requirements stated that that aspiration will be a new aircraft for space tourism, specifically an all-body rocket-powered single-stage to suborbit vehicle capable of going beyond the Kármán line with 6 passengers. Aspiration will employ horizontal takeoff landing methods and will be designed to operate in and out of airports such as the Mojave Air and Spaceport. The space tourism industry is expecting an economic boom over the next few decades. Currently, companies based in America dominate the space tourism market, and main competitors are Virgin Galactic, Blue Origin, and SpaceX. With the available spaceports and launch sites, Aspiration will be able to serve across the world with the future possibility of point-to-point transfer. Target markets for this sector include not only microgravity research, but also other important niches like astronaut training and experimental technology tests. Now we'll move on to parametric sizing. Parametric sizing will be the first step in determining basic aircraft characteristics. It'll give a first-order approximation of our vehicle.
Here's the literature review that was conducted by the synthesis discipline. Next slide. From the results, next slide. Yep, there we go. From the results of our literature review, hypersonic convergence was chosen to size aspiration. This allowed for an integrated vehicle geometry to be created. The process resolves around solving a weight and volume budget equation until the takeoff gross weight and planform area of the vehicle converge. This allows for a wide variety of configurations to be quickly tested by changing a few input parameters. Next slide, please. Here, the parametric sizing MDA can be seen, which implements hypersonic convergence. The end result of this MDA will be a solution space which visualizes all possible design points and viable design points with the lowest possible takeoff gross weight selected. The variety of design points are created by iterating the slenderness of the vehicle, the fuel fraction of the vehicle, and the number of passengers that will be carried by the vehicle. Next slide.
SK, you're muted.
Sorry, thank you. Using this methodology listed earlier in the slide, solution space was created and a small sector of the solution space, 9.61% to be exact, which is situated below the red constraint plane, contained all of the possible configurations for aspiration. It contained varying takeoff gross weight, planform, and weight ratio numbers, along with tau and passengers. This methodology was verified by using the Spaceship 2 data and X-24B data. The design point was calculated to have around 22,881 kilograms as takeoff gross weight with 74 meters per planform and 0.4 fuel fraction. Now moving on to configuration layout. This phase will explore different aircraft configurations with the design point obtained from parametric sizing. With the design point from parametric sizing, an MDA was created to highlight the configuration layout methodology. Rapid CAD prototyping was heavily used for visualizing different configurations, and methodologies generated by the individual disciplines were utilized to validate the configuration according to the mission requirements.
Hello, ladies and gentlemen. I have the privilege of explaining how the geometric features of the aspiration came to be. To begin, the geometry team considered some critical design questions. Some of the foremost questions on our minds as the engineers of this experience were those of the cabin configuration design. Is it volumetrically efficient? Are our passengers comfortable? And how much space is there? To see how these questions might be answered, we compiled a detailed literature review supported by research and well-known aerospace authors. Next slide. From this literature search, a detailed design plan was made, and it is illustrated here. Next slide. Once we made our plan, we had to check that it worked. We used our process to make sure the numbers came out correct for the HL-10, a simple and early lifting buddy aircraft design. It was a success, and the differences between our calculations and the actual known values were within an acceptable margin of error. With our methodology validated and the preliminary sizing finished, the team could move on to the configuration layout phase. Our team iterated through a myriad of different design points, working out mistakes all along the way to refine the design of the aspiration. Next slide. The first design point was developed as a rough outline of the early solution space model obtained by synthesis. The image shown here is a basic concept model obtained from convergence code visualizers. It was dubbed the ice cream cone for how aesthetically unappealing it is, and it barely followed an elliptical shape with an eccentricity of 0.934. Our team had to go back to the drawing board. Next slide. The second design point was characterized by a slimmer profile, but overall increased volume and planform area. However, guidance from our CEO suggested that the shape of the aircraft would be more aerodynamically efficient at lower speeds if it were slightly more angular. Next slide. And thus, the third design point was born, which flattened the shape to use a more trapezoidal cross-section as the base. However, it still had an oversized volume and planform area. While outlining the internal space of the aircraft, the geometry team noticed that the fuel and oxidizer volumes were too small to make any sense. An error was found in the solution space code, which led to a complete overhaul of the design. Next slide. The fourth design point is the penultimate iteration of aspiration, sporting a much smaller volume and area. However, the change in convergence code deemed requisite a change in engine type, since the initial design engines had a lackluster thrust profile. After this long and arduous journey, the Reach Orbitals obtained its final design point. Ladies and gentlemen, it is my pleasure to introduce to you the RSO aspiration. Next slide. It has a swept-back delta planform design that helps with the flight at higher speeds, and two vertical fins on top to provide stability control. This sleek and stylish profile is sure to carry you to new heights as you reach for the stars. 18 windows allow you to take in the beauty of Earth as you revel in your newfound title of astronaut. A traditional door allows for easy access into and out of the cabin space. Next slide. Detailed specifications are shown here, sporting a 74-degree wing sweep, a TOW of 0.162, and a planform area of 74 square meters. The aspiration is a beauty to behold. It is 15.7 meters long and 7.3 meters of maximum width. Inspirations for our design were the Lockheed Martin X-33 and, in part, the X-24B. Next slide. A 3D printed prototype of the model has been created as well and is exhibited here. And finally, I have the pleasure of introducing you to the end user experience and a world first showing of the cabin interior. Miguel Navarro will be your guide in the next slide.
Welcome to the best experience you will ever have. Here in Reach Suborbitals, the geometry team worked together to build this cabin, calculating every minute detail to enhance your experience. Walking up and opening the door will start your journey into becoming an astronaut. Past the door, you can see that there's empty space. This empty space, due to higher volumetric efficiency, will allow you to experience the full weightlessness once we allow you to unbutton your seatbelts for a free roam experience. Next slide. Past this, you can see 6 seats that are shaped in a B format. This B format has been set up strategically to enhance the experience, the comfort level, and to maximize safety. Each seat will have windows on the roof and to the side to give you multiple viewpoints to see the beautiful blue Earth. We designed the seats to incorporate the highest levels of materials that will make it feel like you're sitting in a luxury car driving on the streets of Dubai. The seat is held up on a titanium composite stand that will keep the seat from experiencing any unnecessary motion. Underneath, a light was added around the floor for an additional light source for when you're moving about. In front of the cabin, the 2 pilots can be seen. These pilots are highly trained and equipped with state-of-the-art equipment to get you to space and back home. Here in Reach Suborbitals, we don't aspire to be better than our competition. We know we have reached that goal. Next slide. We have decided to render the astronaut's point of view to showcase the interior of the cabin. We wait once we get to the door to open up so you can see your dreams to come true. Taking a step inside, you can see the designated space and black carpet that you will be floating above. Countless numbers of windows can be seen for your viewing experience. Now let's find you a seat. We will take off shortly. Next slide. We have decided to section off the spacecraft into 3 sections. The aft, measuring 4.51 meters, will house the engine, landing gear, and both fuel tanks. The center will house the passenger, which has been shown to you. The overall length of the cabin is 6.17 meters. Past the cabin, the remaining 4.903 meters will house the electronic system, the nose landing gear, and RCS thrusters. Next slide, please.
During the parametric sizing and configuration layout phases, two different propellant combinations were examined, the first being liquid hydrogen, liquid oxygen, the second being RP1 and liquid oxygen. Liquid hydrogen and liquid oxygen having a lower average density resulted in a higher fuel volume and a larger vehicle. The RP1 liquid oxygen design that was eventually chosen had a lower fuel volume of just over 9 cubic meters. Next slide, please.
The propulsion and fuel system discipline for the configuration layout phase will now be introduced. The propulsion team complete IDA is shown to the right, where text from Sun and Humble were primarily used to influence our methodology. For the configuration layout phase, critical design questions to be answered were what type of engine is best suited, what propellant can be considered, and how does it impact the vehicle design, and what performance parameters for single-stage vehicles should be emphasized. Next slide. Initially, the propulsion team began with an off-the-shelf database consisting of rocket engines from various manufacturers. Within this database, liquid engines were prioritized as they achieved higher performance compared to their hybrid and solid counterparts. Most of these liquid engines contain the high-performing bipropellant combination of liquid hydrogen and liquid oxygen. Although this propellant combination results in high tank mass and low mass fraction due to its extremely low density, it will makes up for it with its high performance. Because of this, Aerojet Rocketdyne's RL-10A5 and RS-25 engines were two first candidates to power vehicle aspiration. Though it was quickly realized that a middle ground could not be found with our design points, either numerous RL-10 engines could not meet the performance requirements, or the RS-25 was proven to be too powerful for our needs, regardless of its throttle setting. The third candidate was SpaceX Merlin 1D engine, used in the Falcon 9, comprised of kerosene and liquid oxygen propellant combination. Kerosene provides a lower performance than liquid hydrogen. It is significantly denser, requiring smaller and lighter tanks, while also having a relatively low cost in comparison. The Merlin engine also has an advantage in having a wide throttle range, being able to throttle down to 40% by using a stored amount of propellant to adjust turbine power, decreasing the flow of propellant, thus decreasing thrust. This was found to be useful during the takeoff and climb to satisfy the thrust requirements and load factor limitations. With low toxicity and single-stage suitability, the Merlin 1D engine was Reach Suborbital's engine of choice. Next slide.
The tail of a spacecraft is incredibly important for its stability. Therefore, the size and shape of the tail was greatly considered. To determine the area of the tail, we created a big list of similar spacecrafts and identified any strong trends. To determine the geometry of the tail, we wanted to take a closer look at the X-24C and the Dream Chaser, since both vehicles are rocket-powered lifting bodies with similar mission requirements. We knew that the tail had to take a similar form. In addition, the control effectors or flaps seen on the tail were made to be about 1/3 of the area as seen through historical data. The heavy reliance on historical data is acceptable for the initial sizing since most of the research is already done for us. In the end, if our analysis proved that the tail was too big or too small, we can resize it. Next slide.
Now moving on to configuration evaluation, where the design point will be extensively analyzed. This slide highlights the configuration evaluation MDA, where the configurations from the previous MDA are extensively analyzed to obtain in-depth analysis results for the design point. This process will be carried out with the disciplines working closely together and further refining the first-order studies from the previous phases.
The weights team is responsible for anything involving weights, such as gross takeoff weight, operating empty weight, CG location, and how it moves, body inertias, structural weight, etc. The image on the right is the weights IDA, or design plan to calculate all of these important parameters. Next slide. The center of gravity is an important parameter for most, if not all, of the team. It determines the placement of the landing gear and reaction control thrusters, the stability of the vehicle, and used for many other calculations by the team. The CG, as well as the body inertias, can be calculated by reducing all of the major components, such as the landing gear, fuel tanks, passengers, etc., to point masses and measuring from a reference point. A careful eye must be kept on the CG as it moves during the flight, since the stability of the vehicle is heavily dependent upon it. Next slide.
Hi, so a tricycle type landing gear system was used for aspiration, and having the system, the load needs to be appropriately divided amongst the main gear and nose gear. To be able to have ground stability, the nose gear cannot carry less than 5% of the load or more than 20% of the load. The main gear is seen to carry about 80 to 95% of the total load. In my analysis, the nose gears will handle 10% of the load as the main gear takes the rest of the 90%. And knowing these appropriate loads, the main gear and the nose gear could size the tires accordingly. The location of the main gear was constrained by the CG and the angle of attack was seen to be 16 degrees. And having this constraint, the height of the landing gear needs to be greater than 1.3 meters to have a clearance for the back end of the vehicle as it takes off. The track length can now be sized to be 4.25 meters in length, and the placement of the nose gear is placed 8.04 meters from the CG. And knowing this, knowing the track length, it was seen that the overturn angle of aspiration was 36 degrees, which limits the vehicle from tipping over. Now on to the next slide.
Now we'll transition over to the takeoff phase.
During the takeoff phase, the main question that the weights, volume, and structures discipline aims to answer is what is the takeoff gross weight of the vehicle? Two methods were examined to determine the takeoff gross weight. The first was using a log-log relationship between the operating empty weight and takeoff gross weight of the vehicle, or using a buildup of the operating empty weight to estimate that takeoff gross weight. The buildup of the operating empty weight was selected to estimate takeoff gross weight, and this method was verified using the X24B. Next slide, please. The first step of building up the operating empty weight was to determine the structural weight. This was done using empirical relationships for lifting body vehicles. The structural weight was found to be 4,177 kilograms, with 92% of this weight being made up by the fuselage of the vehicle. The material of the structure is aluminum. Next slide, please. The remaining components of the vehicle were also calculated using empirical relationships found for lifting body vehicles. Next slide, please. These weights were then summed to get an operating empty weight of just over 13,000 kilograms, which represents a growth of 448 kilograms over the parametric sizing operating empty weight, which is within the 5% target that was set for the weights discipline. Next slide, please. To finish off the estimate of takeoff gross weight, the payload weight and the propellant weights were also calculated with a final takeoff gross weight value of 23,124 kilograms calculated, which represents an increase of 243 kilograms over parametric sizing, which was also within the 5% difference set as a target value. Next slide, please.
And here we have the IDA, which is the technical map that the propulsion team took to find key parameters for the propulsion discipline. The Merlin 1D is an engine that has been used and its performance can be found through literature but has to be evaluated for this spacecraft. This is done by finding the thermochemistry values such as the pressure and temperature the fuel reacts in at the required altitude. This is passed on to nozzle flow. Through nozzle flow equations, we can find parameters such as thrust and ISP. With thrust, the mass flow rates or how much fuel is being used is calculated. The performance team looking at historical data for the Merlin told us to acquire the data at the lowest throttle setting. Next slide. Through the process outlined before, these thermochemistry numbers on the top right are used and we can see the thrust acquired at the lowest thrust setting is 257.7 kilonewtons. The ISP is calculated to be 304.8 and the mass flow rate is 86.176 kilograms per second. Next slide.
During takeoff, the aerodynamics of the aspiration are critical. Major questions must be answered. Will there be a sufficient lift to take off? Will this lift generate too much drag? And can we keep going after the takeoff? To answer these questions, we must take in the flight conditions for takeoff and the geometry of the aspiration. This information can be used to output a parametrically sized VSP model, which will help us produce the aerodynamic coefficients and forces and moments due to the flow. Next slide. The process of creating a parametric model involves setting custom parameters based on design requirements of the aspiration. This model can be run through the OpenVSP aerodynamic tools. A parametrically sized model makes for quick and efficient changes, and so aerodynamic analysis of every iteration of the aspiration is easy. Next slide. The data output from the OpenVSP parametric model must be validated before it can be used. The values are plotted against historical methods for analytical aerodynamic values. The VSP model will be able to output the primary forces, moments, as well as lift and drag coefficients. Shown here is the validation of the lift and drag terms at a range of Mach values and shows accuracy throughout the phase. Next slide. Now that the process has been validated, it may be used to display the takeoff analysis. The takeoff phase is critical as it is the lowest speed with the highest weight, requiring the most lift to continue. This shows the aspiration's possible solution regions for takeoff where excess lift is successful and the intersection is optimal. We are confident that the aspiration is able to take off based on this analysis. And next slide, please.
Hi, in the takeoff analysis for trajectory and performance, some crucial questions must be answered, like the transition to climb altitude, the takeoff field length, and the velocity at liftoff. Therefore, on to the next slide. The takeoff analysis for aspiration started by knowing that the Merlin 1D engine can be operational at 40% thrust. Therefore, the speed of the vehicle can be calculated along the runway. The speed of the vehicle along the runway accounted for the drag force along with the friction force of the landing gear. Aspiration was seen to reach a Mach number of 0.316 for the takeoff speed. The total ground distance was calculated to be 884 meters in length. The passengers don't feel any G's greater than 0.64 at the end of the runway, and the angle of attack was seen to be 16 degrees in correspondence with the lift velocity of aspiration. Now, the transition to climb maneuver was seen to take 5 seconds to start the climb at an altitude of 1 kilometer. Now passing it on to stability.
For any airplane or spacecraft to be stable, the vehicle must have the tendency to return to its initial orientation after some disturbance or gust of wind. Essentially, the vehicle must produce a restoring moment that rotates it back to equilibrium. With data obtained from the aerodynamics team, we were able to generate these plots that would help us determine if the vehicle is inherently stable or unstable. For takeoff, 3 flight conditions were selected to be analyzed. The top left graph is the pitching moment as a function of angle of attack and must have a negative slope, which it does. The middle left graph is the yawing moment as a function of side slip angle and must have a positive slope, which it does. And lastly, the bottom left graph is the rolling moment as a function of side slip angle and must have a negative slope, which it does, meaning that aspiration is stable for takeoff. Next slide.
According to Federal Aviation Regulations, Section 25 requirements, the takeoff phase needs to have takeoff and climb velocities that are small multiples of the stall velocity, and there must be clearance above 10.688 meters. These requirements are satisfied by the aspiration, and with this verified, we can move on to the next phase.
To aid in the configuration evaluation stage of conceptual design, our team developed and utilized our simulation discipline. Before you on the right is our individual disciplinary analysis based on the work of David Allerton, author of Principles of Flight Simulation. And on the left is a small sampling of the software that our team developed to simulate our spacecraft, which will be visualized using the open source software FlightGear. Throughout the remainder of the presentation, I will have the pleasure of joining you as we dive into the exciting world of suborbital space tourism with Reach Suborbitals. Ladies and gentlemen, we begin at Mojave Air and Spaceport, located in Mojave, California. If the guests would please take their seats and strap in, we are about to embark on the journey of a lifetime. In just a few short minutes, you will be floating amongst the stars. We promise our destination is out of this world.
Now transitioning over to the climb phase.
Having selected the most appropriate engine during configuration layout, the power descent configuration evaluation focuses on answering critical questions like what will be the thrust and specific impulse profiles as a function of altitude, how many engines will be required, and if a throttle mechanism will be required for the power descent. Next slide. To answer these questions, the thrust and specific impulse profiles at 100% capability were determined based on the propellant thermochemical properties and the physical characteristics of the nozzle. Working closely with trajectory and performance, the ascent of a single engine and maximum power was tested, and it was identified that even though a single engine was capable of satisfying the altitude mission requirement, it did not satisfy the maximum acceleration constraints, meaning that it will be required to throttle the engine. Results from analyzing the thrust to total vehicle weight ratio and the ascent performance indicated that throttling the mass flow rate intake below 65% will result in a vehicle not being able to accelerate and ascend, while the throttling above 75% will exceed the load limit. Consequently, the engine throttling was selected to 70%, resulting in the mass and thrust properties shown in the table to the right. Next slide.
During climb, the aerodynamics of the aspiration are less critical than takeoff, but there are still major questions to be answered. Can the aspiration generate enough lift to rotate through the pull-up maneuver? And can it have sufficiently low drag for the near vertical flight path? The inputs necessary are the flight conditions and limitations for the drag value based on the thrust available, as well as the model from the takeoff phase. Then the outputs are the aerodynamic coefficients as well as the geometric adjustments where necessary. Next slide, please. Using the parametric model from takeoff, the coefficients can be found for the climb conditions and validated using historical methods. The high-speed flight conditions show drag errors as more refined OpenVSP methods are used. Next slide, please. After validation, the climb aerodynamics can be visualized as drag and thrust over a range of Mach values and angles of attack. This shows the aspiration's ability to accelerate upwards without excessive drag during the climb phase. Next slide.
Knowing the platform area, the initial weight for climb, and the propulsion and aerodynamic profiles during descent, it was then possible to develop trajectory analysis for aspiration. The focus of this analysis was to answer the critical questions of what the main engine cutoff altitude must be in order to reach space, and if the maximum load factor constraint is satisfied for customer commodity by generating the trajectory map, the load factor behavior, and other performance characteristics. Next slide. Using the energy state approximation method, we had an initial Mach number of 0.35 at 1 kilometer as identified from the trajectory and performance takeoff analysis, and accounting for the maximum load factor constraint, among others, the main engine cutoff altitude was determined to be at 46 kilometers at Mach 3.52. From the energy state approximation method, it was identified that to reach space, an energy height of at least 100 kilometers must be obtained. Since such energy height is reached, as shown with the rate energy height contour in the figure to the right, it was concluded that the current power descent trajectory will enable aspiration to reach space with a maximum load factor of 2.8, thus satisfying all the requirements. Next slide.
The same stability analysis from takeoff will be applied to the climb phase. In this phase, we identified 9 important flight conditions. On the top left graph, all the slopes are negative. In the middle left graph, all the slopes are positive. And in the bottom left graph, all the slopes are negative, meaning that all the flight conditions satisfy the static stability requirements. Again, on the plots on the right signify the control power of the control effectors, meaning that the vehicle is still able to steer itself without being too stable. Next slide.
For the aerothermal analysis of the aspiration, more questions must be answered. How much heat will be generated? How hot will the skin of the aircraft get? And will this be a limiting factor for trajectory? In order to answer these questions, some values must be known, like the flight conditions and the geometric properties of the aspiration. These will allow for the output of the overall heat flux into the skin, or the energy applied at the surface, and the temperature history of the flight phase. Next slide. A transient temperature estimation tool was developed that uses the balance of energies in the flow and an arbitrary body with known material properties to yield a temperature history of the input flight conditions. The method relies on the idea that high-speed flow will compress, heat up, and apply convective heat to the surface. The temperature of the surface is then validated with a measured temperature history of the X15, and this shows accurate peak values and rough transient accuracy. Next slide. Using the validated transient tool, a part of the aspiration may be analyzed under a calculated trajectory analysis to get an idea about peak temperatures and heat flux throughout the flight. This shows the result of such an analysis with the start at the front of the climb phase and ending with apogee. This analysis shows an ability to withstand climb easily without considerable compromise to the current model. Next slide.
Looking back to those FAR 25 regulatory requirements, the climb phase needs to have a climb gradient above 91.4 meters per minute since it weighs above 2,721 kilograms. It has a climb gradient of 289 meters per minute, so that's way above. And once again, the aspiration passes with flying colors. With this verified, we can now evaluate the coast phase.
Passengers are reminded to please sit back with your chairs in the upright position to avoid redout while we propel you vertically to Mach 3.2 with the main engine cutoff at 40 kilometers. For your pleasure and comfort, we will maintain acceleration with our Merlin 1D rocket below 3 Gs for the duration of the climb.
Now transitioning over to the coast phase.
The trajectory analysis of the unpowered coast is arguably one of the most important analyses throughout the mission profile, as this is the experience the customer is paying for. Consequently, critical questions like how long will the microgravity experience last and what will the apogee altitude be needed to be answered. The goal was to achieve a higher apogee altitude and a longer unpowered coast time with respect to Spaceship Two and other space tourism companies in the market. Next slide. The unpowered kills analysis was performed using the projectile motion analysis as the vehicle mass is constant and no thrust is being generated. The unpowered kills analysis indicated that aspiration experiences an apogee altitude of 111 kilometers with a time to apogee of a little more than 110 seconds, which results in a total microgravity time of about 4 minutes due to the parabolic behavior. Nominal trajectory analysis of Spaceship Two indicated that the vehicle reaches an apogee altitude of 103 kilometers with a time to apogee of around 100 seconds. Consequently, customers, now astronauts, flying with aspiration will reach higher altitudes for a longer time. Next slide.
Due to the rapid drop in air density above 40 kilometers, conventional control surfaces lose their ability to provide pilots with the control of the spacecraft, so we must rely on reaction control system to augment control power. Here we can see two animations. On top is Boeing Starliner demonstrating the use of reaction control thrusters, while below we see the three axes with which aspiration must be controlled: roll, pitch, and yaw. On the left, we see the moment arms created by the placement of the reaction control system thrusters, which, due to the placement of the yaw thrusters, has become coupled with the roll axis. Based on design criteria for the X-15, the desired angular acceleration rates were chosen, and from those rates, the required thrust force was derived.
Like Ben mentioned, RCS thrusters are used in spacecraft to enhance the level of control. The CHT-400 is chosen because it is a lightweight, it is small, and has one of the best thrust-to-weight ratios compared to other thrusters. As can be seen from stability and controls, two thrusters are placed on each side of the nose on a basis of 3,500 newtons of need. For pitching and for roll, they're placed on the side in front of the wings. Producing 400 newtons, multiple of these thrusters can meet the control requirements, which has been found to be better than implementing one massive system. It has flown more than 30 times with the Ariane 5 during its ascent phase, which can weigh up to 170,000 kilograms, which shows us its reliable system. Next slide.
Ladies and gentlemen, on behalf of all of us here at Reach Suborbitals, I would like to present to you your commercial astronaut badge in recognition of your intrepid exploration of space and the final frontier. And in addition to exceeding the von Karman line, please feel free to float about the cabin and enjoy the magnificent and breathtaking view of our beautiful blue planet.
Now transitioning over to reentry.
A huge role in the reentry phase, aerodynamics makes up two of the three forces acting on aspiration during the unpowered flight half of aspiration's journey back to Earth. A big factor in the reentry analysis is whether or not the vehicle produces enough drag during reentry in order to slow the vehicle down enough before landing. The analysis methodology IDA to quantify this was solidified across a semester of research. Next slide. The analysis methodology was verified to show good agreement between analytical methods and known data. The lift and drag of the vehicle was calculated as a function of altitude. This showed aerodynamic effects beginning to only start to affect the vehicle at 75 kilometers. Next slide. From here, the important aerodynamic parameters were calculated. The lift, drag, and aerodynamic efficiency profiles were calculated for the trajectory of reentry up until glide. Drag reaches its peak just before the pull-up maneuver where the glide phase begins, bleeding off enough of aspiration's energy for glide and landing. Next slide.
The reentry trajectory phase aims to answer critical questions such as what will be the maximum G's experienced by our passengers and what will be the duration of the reentry trajectory. To the right is the reentry IDA methodology influenced by John Adams' atmospheric reentry research. The IDA helps answer the critical questions where the main inputs for the reentry phase is our vehicle's dimensions and weight, entry velocity, and aerodynamic coefficients. The primary outputs are various performance profiles. Next slide. Beginning from apogee, our vehicle behaves like a point ballistic mass in free fall. Using the empty mass, reference area and length, and drag coefficient, the ballistic coefficient could be found, the primary parameter driving ballistic reentry. Coming in at an 81-degree flight path angle, speed and load factor begin to rapidly increase. Roughly 35 seconds in, our vehicle has gone from 75 to 45 kilometers, now at Mach around 3.4. Next slide. Switching from pure ballistic entry to a lifting entry, our vehicle begins a pull-up maneuver. With speeds reaching Mach 4 and plunging into the denser parts of the atmosphere, our primary goal is to stay within the 5G constraint for the safety of our passengers. After 60 seconds and experiencing a maximum of 4.8 Gs, during pull-up, we have descended down to 7 kilometers, concluding the re-entry trajectory. Next slide.
During the reentry phase, the pitching, yawing, and rolling moment coefficients plotted against angle of attack and side slip angle are shown in the following plots for 4 flight conditions. The moment coefficients with respect to elevator, rudder, and aileron deflections can also be seen on the right. These plots represent the control power of the control surfaces. These stability plots were generated using aerodynamic data. Since all static stability criteria is met, we can say that the aspiration is longitudinally, directionally, and laterally stable for all flight conditions during the reentry phase. Passing the presentation off to the next discipline.
This is the aerothermal reentry IDA. It outlines the analysis process that was followed for calculating the heating during the reentry phase. The inputs are the flight profile and the vehicle geometry. The key heating parameters that must be estimated are the maximum temperature and heat flux. Next slide. An analytical tool was developed and validated using X15 flight test data. This tool estimates the heating and it is compared to resolve the error. The error was found to be between 6 to 11%, which is well within the estimated values for the tool. Next slide. A trajectory heating prediction was developed to estimate where the top heating occurs along the trajectory. It was found that the maximum temperature was 500 degrees Celsius at around 15 kilometers and a Mach number of 3.8. Next slide. The transient analysis shown here accounts for the heat being dissipated as time progresses. This is a more accurate method than the one shown previously. With this method, it was estimated that the maximum temperature would be 465 degrees Celsius, and this would occur about 350 seconds into the flight. Next slide.
As a benefit of moderate Mach numbers, aspiration endures relatively low heating and thus requires only a simple thermal protection system. The material chosen was the NASA Advanced Flexible Reusable Surface Insulation, or AFRSI. AFRSI offers a number of advantages when compared to other options. As a lower temperature TPS material, it is easier to maintain as well as install. There are no tiles to worry about either since it is a woven fabric. Based on the data received from Jared and Josue from Aerothermal, a worst-case heating scenario was made and the TPS material thickness was sized accordingly using one-dimensional analytical techniques. Next slide.
Now for the most heart-racing, blood-pumping, and exhilarating moment of our adventure as we hurtled towards the Earth at the breakneck speed of 1,200 meters per second, we approach the 4G pullout. Ensure your seats are fully reclined for proper G orientation. Relax and enjoy the rush.
Transitioning over to glide.
For the unpowered glide phase, all the fuel and oxidizer are depleted. Therefore, the center of gravity location will not shift significantly after engine cutoff. Center of gravity location is a function of the component weights and the component locations. For the X position of the center of gravity, it's measured with respect to the nose, and the Z position of the center of gravity is measured with respect to the bottom of the fuselage. The center of gravity location and body inertias for the aspiration for the reentry phase are shown in the tables below. Passing the presentation off to the next discipline.
This is the aerodynamics glide IDA. It outlines the process used to estimate and validate the glide profile. The inputs are the flight profile and the geometry in order to estimate the aerodynamic properties. The key performance parameter to verify is the glide trajectory with the available aerodynamic performance. Next slide. A numerical tool was validated to accurately predict the aerodynamic properties for the vehicle at multiple flight conditions. Next slide. An aerodynamic database was developed for multiple flight conditions, and the control surface deflections were also modeled for the stability and control and trajectory and performance disciplines. Next slide. The glide trajectory is primarily dependent on the lift to drag ratio. An analysis was performed to determine whether the desired trajectory was feasible. As long as the black line shown in the figure on the right remains on top of the colored surface, the glide trajectory is feasible. And as can be seen, the glide will be successful. Next slide.
The unpowered glide phase aims to answer questions such as at what rate will the vehicle descend, what will be the duration of the glide, and what is the maximum range through the glide phase. To the right is the IDA methodology influenced by text from Roscoe, Phillips, and Nikolai. Using the IDA to aid in answering the critical questions, vehicle dimensions, previous flight phase conditions, and aerodynamic coefficients are all inputs required to output the altitude profile, vehicle glide range, and rate of descent. Next slide. Continuing immediately after its pull-up maneuver, the glide phase begins at an altitude of 7,063 meters with a Mach of 0.8. To meet its target altitude of 200 meters, the vehicle's lift-to-drag ratio is used to minimize the rate of descent, and its flight path angle is used to maximize glide range. Throughout the glide trajectory, the vehicle's flight path angle changes ever so slightly, ranging from 4.5 to 5 degrees, achieving a rate of descent of 12 meters per second and a maximum glide range of roughly 85 kilometers. After 11 minutes, the vehicle slows to a Mach of 0.2 and reaches an altitude of 200 meters, reaching its target altitude and velocity, concluding the glide trajectory. Next slide.
During the unpowered glide phase, the pitching, yawing, and rolling moment coefficients plotted against angle of attack and side slip angle are shown in the following plots for 9 flight conditions. The moment coefficients with respect to elevator, rudder, and aileron deflections can also be seen. These stability plots were generated using aerodynamic data. Since all static stability criteria is met, we can say that the aspiration is longitudinally, directionally, and laterally stable for all flight conditions during the unpowered glide phase. Passing the presentation off to the next discipline.
Fellow astronauts, it has been a pleasure and an honor to spacewalk with you here today among the heavens. We will soon be landing, but for now, we ask that you take a moment to relax and reflect upon the astonishing experience that you have partaken. From this day forward, when you look up at the stars, you will know they will always be within reach, with reach suborbitals.
Now transitioning over to the landing phase.
Once the landing gear is deployed, the center of gravity location will shift, as well as the body inertias. Upon deployment of the landing gear, the center of gravity shifts back and shifts down slightly. Also, upon landing gear deployment, the body inertia about the rolling axis increases, and the body inertias about the yawing and pitching moment axes decrease. The center of gravity location and body inertias for the aspiration during the landing phase are located in the tables shown to the right. Passing the presentation off to the next discipline.
This is the aerodynamics landing IDA. The inputs are the flight profile and the vehicle geometry. The key parameter to estimate are the ground effect and the landing gear implications into the aerodynamic properties, and to ensure the wing is correctly sized for landing. Next slide. The main aerodynamic parameters are estimated with the same tool as for the glide trajectory. However, when the vehicle flies very close to the ground, it experiences a lift increase and a drag decrease due to ground effect. The model shown here can correctly estimate the ground effect aerodynamics for an F-15 based on its flight test data. Next slide. The ground effect does not become significant for a vehicle until a height of about 5 meters off the ground. This ground effect causes a 26% improvement in aerodynamic efficiency. As far as the landing gear goes, the drag was estimated based on existing vehicle data. It was determined that when deployed, the landing gear will exert a 15% increase in the total vehicle drag. Next slide. The actual landing procedure is a very delicate balance of weight, aerodynamic lift, and airspeed. The analysis shown here was developed to help understand how changes in vehicle weight and landing speed can affect different landing capabilities. As is shown in the figure, aspiration has a wide range of landing scenarios. Next slide.
Hi, in the landing analysis for trajectory and performance, some crucial questions must be answered, like the approach velocity and the landing field length to bring aspiration to a complete stop. Therefore, on to the next slide. The landing phase analysis for aspiration is determined right after the end of glide flight. The components needed to begin the approach need such variables such as lift and drag forces upon the vehicle. This can be determined by providing a Mach number, angle of attack, and altitude for the vehicle. In doing so, in my analysis, aspiration starts its approach at an altitude 200 meters above the runway. Aspiration has an approach velocity of a Mach number of 0.22 at an angle of attack of 14 degrees. The next part of the landing phase is the flare maneuver, which is going to start 238 meters away from the runway. Once at touchdown, the vehicle is going to slow down to a speed of 66 meters per second. After this, the aspiration will start its free roll of 200 meters, and then the brake system will kick in. Therefore, the aspiration braking distance will be 367 meters long around the runway until it comes to a complete stop. In the upper right-hand corner describes 3 situations of what the landing could be, but a best situation is posted as good on the table. On to the next slide. The trajectory analysis for all the mission phases were collected by TNP lead engineer Henry to show the total trajectory of aspiration. Now on to the next slide for certification.
Confirming Pablo's work, the final certification of the aspiration is completed with the FAR 25 regulatory requirements for the landing phase. Velocity at approach and touchdown must be small multiples of the stall velocity, and the landing distance must facilitate a clearance of 15.24 meters. As can be seen, aspiration is a fully certifiable vehicle according to FAR 25. Next slide.
The IDA for cost, safety, and certification are combined into one master IDA to ensure that the design point follows all safety certification protocols while ensuring the an affordable space tourism experience. To estimate how much that space tourism flight costs, the TransCost model was used to determine its direct operating costs, the development cost, manufacturing costs, as well as operating costs. The TransCost model was used, and the Spaceship 2 data was used to validate or verify those methodologies. The TransCost model provided promising results. We first calculated the airframe development cost along with other manufacturing costs, and since we were buying a commercially off-the-shelf engine, we didn't need to develop an engine development cost. According to that figure, you can see that the break-even points are shown according to with the number of flights on the x-axis and the revenue being generated on the y-axis. The break-even analysis gave us results that said that the number of flights, if for one aspiration flight, if we fly that one aircraft for around 1,500 flights for a ticket price of about for $200,000 per seat, we'll break even in 1,500 flights, and the launches per year rate was set to 220. And that concludes our presentation. Thank you for listening in today, and that's about it.